Artemis, humanity's return to the moon. Close your eyes and imagine standing on the surface of the moon. The ground beneath your boots is gray and powdery, ancient dust that has lain undisturbed for billions of years. Above you, in the black velvet sky, Earth hangs like a blue and white marble, impossibly beautiful, impossibly fragile. Oh, you are 238,000 miles from home, standing where only 12 human beings have ever stood before. The year is 2029, and you are part of the Artemis program, humanity's return to the moon after more than half a century away. But this story does not begin in 2029. It begins much earlier, in the depths of the Cold War, when two superpowers raced to prove their technological supremacy by conquering the heavens. It begins with a challenge issued by a young president who promised to land a man on the moon and return him safely to Earth before the 1960s ended. It begins with Apollo. On May 25, 1961, President John Fitzgerald Kennedy stood before a joint session of Congress and delivered one of the most audacious proclamations in human history. The Soviet Union had already shocked the world by launching Sputnik, the first artificial satellite, in 1957. They had sent the first living creature into orbit, a dog named Laika, shortly thereafter. And on April 12, 1961, just weeks before Kennedy's speech, Soviet cosmonaut Yuri Gagarin had become the first human being to orbit the Earth. The United States was losing the space race, and Kennedy knew that American prestige and global leadership hung in the balance. "I believe," Kennedy declared, his Boston accent crisp and confident, "that this nation should commit itself to achieving the goal before this decade is out, of landing a man on the moon and returning him safely to the Earth." The challenge was extraordinary. At that moment, the United States had conducted exactly one manned space flight, Alan Shepard's 15-minute suborbital hop just 3 weeks earlier. The technology to reach the moon did not exist. The rockets were not powerful enough. The spacecraft had not been designed. The navigation systems had not been invented. Kennedy was promising to accomplish in less than 9 years what seemed impossible. But NASA accepted the challenge. The Apollo program was born, representing the largest research and development project in peacetime history. At its peak, the program employed more than 400,000 people across the United States. It consumed more than half of NASA's entire budget throughout the 1960s. Engineers and scientists worked around the clock, solving problems that had never been encountered before. How do you navigate to the moon? How do you land on a surface no human has ever touched? How do you keep astronauts alive in the hostile environment of space? How do you bring them home again? The path to the moon was paved with both triumph and tragedy. On January 27, 1967, during a routine ground test, a fire broke out in the Apollo 1 command module. Astronauts Virgil, Gus Grissom, Edward White, and Roger Chaffee were killed instantly, trapped inside as flames consumed the pure oxygen atmosphere. The nation mourned, and the program nearly died with them. But NASA persevered, redesigning the spacecraft to make it safer, more reliable, more worthy of the men who would risk their lives inside it. The missions that followed built toward the ultimate goal in careful increments. Apollo 7, in October 1968, tested the command module in Earth orbit. Apollo 8, just 2 months later, became the first crewed spacecraft to leave Earth orbit and travel to another celestial body. Astronauts Frank Borman, James Lovell, and William Anders orbited the Moon 10 times on Christmas Eve 1968 and transmitted live television images back to Earth. As Earth rose above the lunar horizon, Anders captured one of the most iconic photographs in history, Earthrise, showing our planet as a fragile blue oasis in the darkness of space. The astronauts read from the book of Genesis as they looked down on the lunar surface, and more people watched and listened than had ever witnessed a single event in human history up to that point. Apollo 9 tested the lunar module in Earth orbit in March 1969. Apollo 10 in May 1969 was the dress rehearsal. Astronauts Thomas Stafford and Eugene Cernan descended in the lunar module to within 50,000 feet of the Moon's surface, close enough to map the terrain for the landing that would come next, close enough to feel the pull of lunar gravity. But they did not land. That honor was reserved for Apollo 11. On July 16, 1969, a Saturn V rocket lifted off from Launch Complex 39 at Kennedy Space Center in Florida. Atop that rocket sat Apollo 11, carrying 3 men toward destiny. Commander Neil Armstrong, Lunar Module Pilot Edwin Buzz Aldrin, and Command Module Pilot Michael Collins had trained for years for this moment. The launch was perfect. The trans-lunar injection burn flawless. 3 days later, as Armstrong and Aldrin prepared to descend in the lunar module named Eagle, Collins remained in the command module Columbia, orbiting alone above the lunar surface. The landing was anything but smooth. The Eagle's computer guided them toward a crater filled with boulders. A landing there would have been catastrophic. Armstrong took manual control, flying the lunar module like a helicopter, searching for a smooth spot as fuel ran dangerously low. Mission Control in Houston watched the telemetry with mounting tension. Alarms sounded in the cockpit. With less than 30 seconds of fuel remaining, Armstrong found a clear area in the Sea of Tranquility and set Eagle down. Houston, Armstrong's voice crackled across 250,000 miles of space. Tranquility Base, here. The Eagle has landed. Roger. Tranquility, came the reply from Houston, where controllers had been holding their breath. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. 6.5 hours later, Armstrong opened the hatch and descended the ladder. A television camera mounted on the lunar module transmitted grainy black and white images to Earth, where 600 million people, nearly 1/5 of the entire human population, watched as Armstrong stepped off the ladder's final rung and placed his boot on lunar soil. That's one small step for man, Armstrong said, though a technical glitch ate the article. That he later insisted he had spoken. One giant leap for mankind. Aldrin joined him 20 minutes later, and together they spent 2 hours and 32 minutes on the surface. They planted an American flag, collected 47.5 pounds of lunar rocks and soil, set up scientific experiments, took photographs, and spoke by telephone with President Richard Nixon. Then they returned to Eagle, lifted off from the Moon, rendezvoused with Collins in Columbia, and headed home. On July 24th, 1969, they splashed down in the Pacific Ocean. They had done the impossible. 5 more Apollo missions successfully landed on the Moon. Apollo 12, in November 1969, demonstrated precision landings by touching down within 600 feet of the Surveyor 3 probe that had landed 2 years earlier. Apollo 13, in April 1970, suffered an oxygen tank explosion that nearly killed the crew. But through brilliant improvisation by the astronauts and ground controllers, James Lovell, Fred Hayes, and Jack Swigert made it home alive. Apollo 14, 15, 16, and 17 explored increasingly ambitious landing sites, stayed longer on the surface, traveled farther in lunar rovers, collected more samples, and conducted more science. Apollo 17, in December 1972, was the final mission. Astronauts Eugene Cernan and Harrison Schmitt, a professional geologist, the only scientist to walk on the moon, spent 3 days exploring the Taurus Littrow Valley. When Cernan climbed back into the lunar module for the last time, he spoke words that would hang over humanity for more than half a century. As we leave the moon at Taurus Littrow, we leave as we came, and God willing, as we shall return with peace and hope for all mankind. But humanity did not return. The final 3 planned Apollo missions, 18, 19, and 20, were cancelled due to budget cuts. The Vietnam War was consuming vast resources. Social programs needed funding. The public, having watched 6 successful moon landings, had lost interest in space exploration. The Saturn V rockets and Apollo spacecraft were repurposed. Skylab, America's first space station, used Apollo hardware. The Apollo-Soyuz test project in 1975 linked an Apollo capsule with a Soviet Soyuz spacecraft in orbit, a symbol of Cold War détente. And then the Apollo program ended. The last Saturn V rocket was launched in 1973. The last Apollo spacecraft flew in 1975. For more than 50 years, no human ventured beyond low Earth orbit. The Space Shuttle program, which flew from 1981 to 2011, was magnificent, but constrained to orbits just a few hundred miles above Earth. The International Space Station, assembled beginning in 1998, orbited at an altitude of just 250 miles, less than 1/1000th the distance to the moon. Plans for a return to the moon came and went. President George H.W. Bush proposed the Space Exploration Initiative in 1989, including moon bases and Mars missions, but it died in Congress due to cost estimates exceeding $400 billion. President George W. Bush announced the Constellation program in 2004, with plans to return to the moon by 2020, but President Barack Obama cancelled it in 2010 due to cost overruns and schedule delays. And then came Artemis. The Artemis program emerged from the ashes of Constellation, taking shape gradually through the early 2010s. The NASA Authorization Act of 2010 mandated the development of a new heavy-lift rocket and crew capsule capable of missions beyond low Earth orbit. These became the Space Launch System, the most powerful rocket NASA has ever built, and the Orion spacecraft, a next-generation capsule designed for deep space missions. But a rocket and a spacecraft alone do not make a lunar program. What was needed was a vision, a plan, and most importantly, political will and funding. In December 2017, President Donald Trump signed Space Policy Directive 1, formally establishing human lunar exploration as a national priority. In March 2019, the Vice President Mike Pence announced an accelerated timeline, declaring that NASA would land astronauts on the moon by 2024. The program would be called Artemis, named after the twin sister of Apollo in Greek mythology. Artemis was the goddess of the moon and the hunt, and the program's name carried symbolism beyond its mythological reference. Artemis would land the first woman on the moon. Artemis would land the first person of color on the moon. Artemis would establish not just a brief visit like Apollo, but a sustained presence with astronauts living and working on the lunar surface for extended periods. The Artemis program represents something fundamentally different from Apollo. Apollo was born from Cold War competition, driven by national pride and geopolitical rivalry. The goal was to get there first, to plant the flag, to prove American technological superiority. Artemis, by contrast, is driven by scientific discovery, economic opportunity, and preparation for even more ambitious goals. The Artemis program is not just about returning to the moon. It is about learning to live and work on another world as preparation for the ultimate destination, Mars. The architecture of Artemis is complex, involving multiple spacecraft, international partnerships, and a phased approach that builds capability over time. At the heart of the program, it is the Space Launch System, or SLS. This rocket is a monster, standing between 322 and 364 feet tall, depending on configuration, taller than the Statue of Liberty. The SLS generates 8.8 million pounds of thrust at liftoff. That is 15% more than the Saturn V that carried Apollo to the moon, making SLS the most powerful rocket ever flown. The SLS is what engineers call a heavy lift vehicle, designed specifically for deep space missions. Its first stage, called the core stage, is a massive cylinder, 64 feet tall and over 27 feet in diameter. Inside are two enormous tanks, one holding 730,000 gallons of liquid hydrogen, the other holding 196,000 gallons of liquid oxygen. These cryogenic propellants, cooled to temperatures of minus 423 degrees Fahrenheit for the hydrogen and minus 297 degrees for the oxygen, feed 4 RS-25 engines mounted at the base of the core stage. The RS-25 engines are marvels of engineering, and they have a distinguished history. These are not new engines built specifically for SLS. They are refurbished engines that flew on the Space Shuttle. Each RS-25 operated with 100% mission success during 135 shuttle flights, more than 3,000 engine starts, over 1 million seconds of test firings and flight operations. The RS-25 is one of the most reliable, most tested, most proven rocket engines ever built. For the early Artemis missions, NASA is using 16 RS-25 engines that flew on shuttles, carefully inspected and upgraded for their new role. After those engines are expended, new RS-25E engines will be manufactured specifically for SLS. Attached to either side of the core stage are two solid rocket boosters, each one 177 feet tall. These boosters are also derived from shuttle hardware, though they have been upgraded with an additional segment, making them 5-segment boosters instead of the shuttle's 4-segment design. Each booster contains 631,000 pounds of solid propellant, a mixture of ammonium perchlorate, aluminum powder, iron oxide, and a polymer binder. When ignited, each booster produces 16 million pounds of thrust. Together with the 4 RS-25 engines, the total thrust at liftoff exceeds 8.8 million pounds, enough to shake the ground for miles around the launch pad. The solid rocket boosters burn for just 126 seconds, providing most of the thrust needed to escape Earth's atmosphere. Then they separate from the core stage and fall away, descending by parachute into the Atlantic Ocean, where they can be recovered, refurbished, and potentially reused. The core stage continues burning for another 6 minutes, carrying the upper stage and Orion spacecraft toward orbital velocity. At an altitude of roughly 100 miles, traveling at more than 15,000 miles per hour, the core stage shuts down and separates, falling back to Earth, where it will burn up in the atmosphere or impact the ocean. Above the core stage sits the upper stage. For the first 3 Artemis missions, this is the interim cryogenic propulsion stage, or ICPS, and essentially a modified version of the Delta cryogenic second stage used on United Launch Alliance's Delta IV rocket. The ICPS is powered by a single Aerojet Rocketdyne RL-10 engine, producing 24,750 pounds of thrust. It fires first to circularize the orbit around Earth, then fires again to send Orion on its trans-lunar trajectory, the path to the Moon. Beginning with Artemis IV, the ICPS will be replaced by the Exploration Upper Stage, or E2S, a much larger and more capable stage. The EUS will be 8.4 meters in diameter, the same as the core stage, and will carry up to 129,000 kilograms of propellant. Powered by 4 RL-10 engines, the EUS will enable more ambitious missions, including direct insertion of heavy payloads into lunar orbit and support for the Lunar Gateway space station. Atop the upper stage sits the Orion spacecraft, humanity's chariot back to the Moon. Orion is NASA's first deep space crew vehicle since Apollo, designed to carry up to 4 astronauts on missions lasting up to 21 days. The spacecraft consists of 3 main components: the crew module, the service module, and the launch abort system. The crew module is where the astronauts live and work. It is cone-shaped, 11 feet in diameter at its base, and provides 316 cubic feet of habitable volume, about 50% more space than the Apollo command module. Inside, the crew module features advanced avionics and displays, environmental control and life support systems, and the largest heat shield ever built for a crewed spacecraft. That heat shield is critical. When Orion returns from the Moon, it will hit Earth's atmosphere at 25,000 miles per hour, nearly 9 times faster than a rifle bullet. The friction of atmospheric entry will heat the heat shield to 5,000 degrees Fahrenheit, hot enough to vaporize steel. The heat shield is made of a material called avcoat, an ablative material that slowly burns away during re-entry, carrying heat away from the crew module and protecting the astronauts inside. Behind the crew module is the European Service Module, provided by the European Space Agency as part of international cooperation on Artemis. The Service Module is the spacecraft's powerhouse, providing propulsion, power, thermal control, and consumables like air and water. Its main engine can produce 6,000 pounds of thrust for major maneuvers like orbital insertion and trans-Earth injection. 32 smaller thrusters provide attitude control and minor corrections. 4 solar array wings, each one nearly 40 feet long, generate 21 kilowatts of electrical power. The service module carries nearly 2,000 gallons of propellant and stores oxygen, nitrogen, and water for the crew. The launch abort system, mounted atop the crew module, is Orion's emergency escape mechanism. If something goes catastrophically wrong during launch, an explosion, structural failure, or loss of control, the abort motor can fire, producing 400,000 pounds of thrust to yank the crew module away from the failing rocket. The abort system can activate automatically or be triggered by the crew, and it can pull the crew module to safety in as little as 3 seconds. Once Orion reaches orbit and the danger of launch is past, the launch abort system is jettisoned, reducing weight for the journey ahead. Together, the Space Launch System and Orion spacecraft form the backbone of the Artemis program, the vehicles that will carry astronauts beyond Earth and toward the Moon. But they are just the beginning of a much larger architecture. The first test of this architecture came with Artemis 1. On November 16, 2022, at 1:47 in the morning, Eastern Time, the Space Launch System lifted off from Launch Complex 39B at Kennedy Space Center. The roar was indescribable. 8.8 million pounds of thrust, translating into sound waves that rattled windows for miles. Flames shot hundreds of feet below the mobile launcher platform. The ground trembled, and slowly, majestically, the 32-story rocket rose into the night sky, its solid boosters painting the darkness with brilliant fire. This was an uncrewed test flight designed to validate every system before risking human lives. The Orion spacecraft carried no astronauts, only 3 mannequins equipped with sensors to measure radiation exposure, vibration, and acceleration. The mannequins had names: Commander Munikin Campos, named after Arturo Campos, an electrical engineer who played a crucial role in bringing Apollo 13 home safely, Helga and Zohar. Helga and Zohar were female torsos designed to measure radiation effects on organs, with Zohar wearing a protective vest to test radiation shielding. The launch was flawless. 8 minutes after liftoff, the core stage shut down and separated. The ICPS fired, placing Orion into a stable orbit around Earth. 90 minutes later, the ICPS fired again for 18 minutes, accelerating Orion to 24,500 miles per hour and sending it on a trajectory toward the Moon. This trans-lunar injection burn was perfect, and Orion left Earth orbit, becoming the first spacecraft designed for human crews to venture beyond low Earth orbit in 50 years. Over the following days, Orion flew toward the Moon, its cameras capturing spectacular images of Earth shrinking behind it and the lunar surface growing ahead. Flight controllers on the ground tested every system: propulsion, power, communications, thermal control, navigation. Everything worked as designed. On November 21st, Orion performed an outbound powered flyby using the service module's main engine to pass just 81 miles above the lunar surface. The burn changed Orion's velocity from 2,128 miles per hour to 5,102 miles per hour, placing it on a trajectory into distant retrograde orbit. A distant retrograde orbit is a unique path around the Moon. Distant because it takes the spacecraft far from the lunar surface, as much as 40,000 miles away, and retrograde because the direction of travel is opposite to the Moon's rotation. This orbit is stable, requiring minimal fuel to maintain, and it allowed Orion to spend time testing systems in the deep space environment. On November 26th, Orion broke the distance record for a spacecraft designed to carry humans, traveling more than 268,000 miles from Earth, farther than any crewed-capable vehicle had ever gone. Orion spent 6 days in distant retrograde orbit, completing half an orbit around the Moon, while controllers continued testing and cameras captured images of Earth and Moon together in the same frame. Our blue world and grey satellite hanging in the void, both crescents of light against the darkness. Then, on December 1st, Orion fired its engine again for another powered flyby, this time descending to just 130 miles above the surface and using the Moon's gravity to slingshot back toward Earth. The return journey took 10 days. During this time, controllers tested Orion's star trackers, reaction control thrusters, and thermal systems. The spacecraft performed perfectly. On December 11th, 2022, exactly 50 years to the day after Apollo 17 splashed down, Orion reached Earth's atmosphere. The service module separated and burned up. The crew module oriented itself with heat shield forward and plunged into the atmosphere at 25,000 miles per hour. For 4.5 minutes, Orion endured temperatures of 5,000 degrees Fahrenheit as atmospheric friction slowed its descent. A communications blackout occurred as ionized plasma surrounded the capsule, blocking radio signals. Then, as speed decreased and plasma cleared, communications resumed. At 25,000 feet, small drogue parachutes deployed, stabilizing the capsule. At 5,000 feet, the drogue chutes cut away, and 3 massive main parachutes opened, each one 116 feet in diameter. Orion descended gently, swaying beneath the orange and white parachutes. At 9:40 in the morning Pacific time, it splashed down in the Pacific Ocean west of Baja California. Recovery ships were standing by, and within hours, Orion was aboard the USS Portland. Artemis 1 was a complete success. Every primary objective was met. The Space Launch System had performed flawlessly, proving itself the most powerful operational rocket in the world. The Orion spacecraft had traveled farther than any crewed-capable vehicle in history, spent 25.5 days in space, and returned safely through the most demanding re-entry conditions any spacecraft must face. The heat shield had protected the crew module, the parachutes had deployed, and every system had worked as designed. Engineers examined every piece of data, every sensor reading, every photograph. They found issues that needed attention. Some anomalous readings from star trackers during thruster firings, unexpected erosion patterns on the heat shield, but nothing that couldn't be understood and addressed. The path to crewed flights was clear. Artemis 2 will be the first crewed mission of the program, scheduled to launch no earlier than April 2026. 4 astronauts will fly aboard Orion on a 10-day mission that will take them farther from Earth than any humans have traveled in over half a century. The crew has been selected and announced. Commander Reed Wiseman, Pilot Victor Glover, Mission Specialist Christina Koch, and Mission Specialist Jeremy Hansen. This crew is historic. Victor Glover will be the first person of color to leave low Earth orbit, traveling beyond the realm where any human of African descent has gone before. Christina Koch will be the first woman to fly beyond low Earth orbit, venturing into territory previously reserved for men. Jeremy Hansen, a Canadian astronaut, will be the first non-American to travel to the Moon, reflecting the international cooperation that defines Artemis. Hansen was assigned through a 2020 treaty between the United States and Canada, part of Canada's contribution to the program. The Artemis 2 mission profile is designed to test all systems with the crew aboard while stopping short of actually landing. After launch and translunar injection, Orion will follow a trajectory called a hybrid free return. This trajectory loops around the moon and uses lunar gravity to slingshot back toward Earth without requiring engine burns. A free return, meaning that even if propulsion systems failed, the spacecraft would naturally return to Earth. But the trajectory is hybrid because it requires 2 orbits around Earth before heading to the moon, allowing the crew to perform system checkouts before committing to the lunar journey. As Orion approaches the moon, the crew will pass through the Van Allen radiation belts, donut-shaped zones of charged particles trapped by Earth's magnetic field. These radiation belts pose a hazard to both electronics and human health, and Artemis 2 will gather detailed data on radiation exposure to inform protection strategies for future missions. Passing the moon at an altitude of about 100 miles, Orion will fly through lunar shadows and back into sunlight, testing thermal systems under the extreme temperature swings of space near the moon. At its farthest point, Orion will travel approximately 8,800 kilometers, about 5,500 miles, beyond the moon, putting the crew 8,889 kilometers from our nearest neighbor, and a total distance from Earth exceeding 400,000 kilometers. This will be the farthest humans have ever traveled from our home planet, breaking the record set by Apollo 13. From that vantage point, the astronauts will see both Earth and Moon as complete spheres, both hanging in space, and they may witness the phenomenon that Apollo 8 astronauts saw: Earthrise, our blue planet rising above the gray lunar horizon. The crew will spend the mission testing every system needed for more complex operations: the environmental control and life support system that generates oxygen, removes carbon dioxide, regulates temperature, and provides water; the propulsion systems that maneuver the spacecraft; the communication systems that link them to Earth; the guidance and navigation systems that know where they are and where they're going. They will test procedures for everything from meal preparation to waste management, from sleeping in microgravity to conducting observations and photography. All of this data will inform planning for Artemis 3 and beyond. After approximately 10 days in space, including the journey out, the lunar flyby, and the return, Orion will re-enter Earth's atmosphere and splash down in the Pacific Ocean. If all goes as planned, the crew will return safely, and NASA will have validated that the Artemis architecture can support human crews on journeys beyond Earth orbit. The path to landing on the moon will be open. Artemis 3 is currently scheduled for no earlier than mid-2027, though this date has already slipped multiple times and may slip again. This will be the first crewed moon landing since Apollo 17, the moment when astronauts once again set foot on lunar soil after more than 50 years. The mission will last approximately 30 days from launch to splashdown, with 2 astronauts spending about a week on the lunar surface. The landing site for Artemis 3 will be near the moon's south pole, a region no humans have ever explored. The South Pole is one of the most intriguing regions on the moon. Orbital reconnaissance has revealed that permanently shadowed craters at the poles contain water ice, frozen water that has lain in darkness for billions of years. Water on the moon is precious beyond measure because water can be split into hydrogen and oxygen. Oxygen for breathing, hydrogen and oxygen for rocket fuel, water for drinking, for agriculture, for radiation shielding. Finding and learning to use lunar water is essential for any sustained presence on the moon. The South Pole also features regions of near-permanent sunlight. Crater rims and mountaintops catch the sun for most or all of the lunar day, providing nearly continuous solar power. These regions of light and shadow, water ice, and solar energy make the South Pole the most attractive location for a lunar base. Artemis 3 will demonstrate the technologies and procedures needed to operate in this challenging environment. 2 astronauts, one of them a woman, one of them possibly a person of color, will transfer from Orion to a human landing system, descend to the surface, conduct 4 spacewalks over their week-long stay, collect samples, set up scientific instruments, and then return to Orion for the journey home. The Human Landing System, or HLS, is being developed by SpaceX. In April 2021, NASA selected SpaceX's Starship as the HLS for Artemis 3, awarding a contract worth nearly $3 billion. This was controversial. SpaceX was competing against Blue Origin and Dynetics, and both losing companies protested the decision. But NASA's rationale was clear. Starship offered more capability at lower cost than the alternatives. Starship HLS is a variant of SpaceX's Starship vehicle, a massive spacecraft over 160 feet tall and 30 feet in diameter. Unlike the standard Starship designed for Earth launch and return, the HLS variant is optimized for the lunar environment. It has no heat shield and no aerodynamic control surfaces because it will never enter an atmosphere. It has large landing legs for stability on the lunar surface. Most critically, it has additional propellant tanks and a completely different mission profile. Getting Starship HLS to the moon is complex. The vehicle cannot launch from Earth and fly directly to the moon. It's too heavy. Instead, a standard Starship will launch from Earth and enter orbit. Then, a series of tanker Starships, at least 14 of them, will launch and dock with the orbiting Starship COHLS, transferring propellant until HLS is fully fueled. Only then, with tanks full, can Starship HLS fire its engines and head to lunar orbit, where it will wait for the Artemis crew to arrive in Orion. When Orion reaches lunar orbit with its crew of 4, 2 astronauts will transfer to Starship HLS through a docking adapter. They will then separate from Orion and descend to the surface. Starship HLS's engines will fire, slowing the vehicle and bringing it down gently to the lunar surface. The spacecraft will land vertically, just as Apollo's lunar module did, but Starship HLS is vastly larger, over 160 feet tall compared to the lunar module's 23 feet. The astronauts will be dozens of feet above the surface, so SpaceX is developing an elevator system to lower them to the ground. Once on the surface, the crew will conduct 4 spacewalks, or EVAs, extravehicular activities. They will wear next-generation spacesuits developed by Axiom Space in collaboration with fashion house Prada. These suits are designed to be more mobile, more comfortable, and safer than the Apollo suits, with better thermal control, improved gloves for dexterity, and advanced materials that can withstand lunar dust. The scientific objectives for Artemis 3 are ambitious. The astronauts will deploy the Lunar Environment Monitoring Station, or LEMS, a compact autonomous seismometer suite that will measure moonquakes and study the internal structure of the moon. They will set up LEEAF, the Lunar Effects on Agricultural Flora experiment, which will investigate how the lunar environment affects plants, crucial knowledge for any future lunar base. They will deploy the Lunar Dielectric Analyzer, or LDA, which will measure the electrical properties of lunar soil, and they will collect samples of regolith, rock, and possibly water ice, bringing them back to Earth for detailed analysis. Before Artemis 3 launches, an unpressurized lunar rover will be delivered to the landing site. This Lunar Terrain Vehicle, or LTV, will allow the crew to travel farther from their landing site than they could on foot, exploring more territory and accessing more diverse geological features. The rover will remain on the moon after the crew departs, available for future missions. After about a week on the surface, the crew will climb back aboard Starship HLS, seal the hatch, and prepare for ascent. The spacecraft's engines will fire, lifting it off the moon and into orbit. There, Starship HLS will rendezvous with Orion. The two astronauts will transfer back to Orion, bringing their samples and data with them. Starship HLS will be disposed of, sent into an orbit around the Sun, in where it will drift forever, a monument to human achievement floating through space. And Orion, with all 4 crew members aboard, will fire its service module engine and head back to Earth. If all goes as planned, Artemis 3 will mark the return of humanity to the lunar surface and the first steps toward a sustained presence. But Artemis 3 is just the beginning. The subsequent missions will build on this foundation, constructing a permanent lunar infrastructure that can support long-term exploration. Artemis 4, scheduled for no earlier than September 2028, will introduce humanity's first space station in lunar orbit, the Lunar Gateway. Gateway is a collaborative project involving NASA, the European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, and the Mohammed bin Rashid Space Center of the United Arab Emirates. It represents the most ambitious international space cooperation since the International Space Station. Gateway will be much smaller than the ISS, about 20 meters long compared to the ISS's 50 meters, but it will orbit the Moon 1,000 times farther from Earth. Unlike the ISS, which is continuously occupied, Gateway will spend most of its time uncrewed, operating autonomously. Astronauts will visit for stays of up to 3 months, using it as a staging point for surface missions, a laboratory for deep space research, and a test bed for technologies needed for Mars missions. Gateway's orbit is unique, a near rectilinear halo orbit, or NRHO. This highly elliptical path brings Gateway as close as 1,000 miles to the Moon's surface and as far as 43,500 miles away. The orbit is dynamically stable, requiring minimal fuel to maintain. When Gateway is at its closest approach to the Moon, crews can easily descend to the surface. When it is farthest from the Moon, Gateway has a clear view of Earth, facilitating communications. The orbit also provides regular periods of near constant sunlight, essential for solar power. Gateway will be assembled in stages over multiple Artemis missions. The first 2 elements, the power and propulsion element, or PPE, and the habitation and logistics outpost, or HALO, will launch together no earlier than September 2028 on a SpaceX Falcon Heavy rocket. Sren, the PPE, built by Maxa Technologies, is essentially a giant solar electric power station, and 2 solar arrays, each about the size of a football field's end zone, generate 60 kilowatts of electricity. This power runs Gateway's systems and feeds the electric propulsion system, which uses ionized xenon gas for thrust, allowing Gateway to maintain its orbit and maneuver when needed. Halo, built by Northrop Grumman, is the first habitation module, based on the company's Cygnus cargo spacecraft that has been delivering supplies to the International Space Station for years. Halo provides living space for 4 crew members during their visits to Gateway. Inside, crew members will find sleeping quarters, life support systems, command and data handling equipment, and a docking port for Orion and other spacecraft. Halo is approximately 23 feet long and 10 feet in diameter, modest but functional. Once PPE and Halo are in orbit and Gateway begins operations, subsequent missions will add more modules. Artemis 4, currently scheduled for no earlier than September 2028, will bring 4 astronauts to Gateway along with the International Habitation Module, or IHAB. This module, being developed through cooperation between the European Space Agency and the Japan Aerospace Exploration Agency, will provide additional living space, an airlock for spacewalks, and more docking ports. With IHAB attached, Gateway will begin to feel less like a cramped outpost and more like a proper space station. Artemis 5 will deliver the European system, providing refueling, infrastructure, and telecommunications, known by the acronym eSPRIT. This module will include a communications antenna to provide high-bandwidth data links to Earth, a viewing window for observations and psychological well-being humans need to see outside, and most critically, a refueling depot. eSPRIT's refueling capability will allow lunar landers and other spacecraft to fill their tanks at Gateway, drastically improving mission flexibility. A spacecraft that arrives at Gateway nearly empty can be refueled for its descent to the Moon, then refueled again for the trip home. This architecture makes Gateway the gas station of lunar space. Future modules under consideration include Canada's contribution, a robotic system called Canadarm3, building on the heritage of the famous Canadarm on the Space Shuttle and Canadarm2 on the International Space Station. This sophisticated robotic arm will be able to capture visiting spacecraft, move equipment, and assist with maintenance tasks operated either by crew aboard Gateway or by controllers on Earth. The Mohammed bin Rashid Space Center of the United Arab Emirates is also contributing, providing the crew and science airlock for Gateway, allowing experiments and equipment to be exposed to the vacuum of space. Gateway represents a fundamentally new model for space exploration. Unlike the International Space Station, which required decades to complete and hundreds of launches, Gateway will be assembled in just a few years with a handful of missions. Unlike the ISS, which orbits just 250 miles above Earth in relative safety, Gateway will orbit the Moon, exposed to higher radiation levels, more extreme temperatures, and the psychological challenges of true deep space. Astronauts aboard Gateway will be farther from Earth than anyone has been since Apollo. If something goes wrong, there is no quick rescue mission. Help is days away, not hours. But Gateway also offers capabilities impossible in low Earth orbit. From Gateway, astronauts can descend to the lunar surface for extended missions, conduct research in deep space without the complexity of landing, test life support systems under conditions similar to those astronauts will face on the journey to Mars, and serve as mission control for robotic explorers across the lunar surface. Gateway is a stepping stone, a waypoint between Earth and wherever humanity ventures next. The Artemis missions following the initial landing will establish a cadence of lunar visits. Current planning suggests annual or biannual missions, with crews spending weeks to months on and around the moon. These missions will follow a pattern: launch from Earth aboard SLS and Orion, travel to lunar orbit, dock with Gateway, transfer to a human landing system, descend to the surface, conduct extensive surface operations, return to Gateway, and finally, head home to Earth. Each mission will build on the last, with new capabilities added incrementally. Future landing sites may include Shackleton Crater, located directly at the lunar South Pole, which has been a target of interest for years due to its permanently shadowed regions containing water ice and its rim that receives nearly constant sunlight. Other potential sites include the peaks of eternal light, mountaintops that catch the sun for 80 to 90% of each lunar day. A base established on one of these peaks would have nearly continuous solar power while having easy access to shadowed craters containing water ice just a short rover drive away. The long-term vision for Artemis includes establishment of a permanent base on the lunar surface. This base, still in conceptual stages, might initially consist of inflatable habitats where astronauts can live for months at a time. These habitats would be surrounded by lunar regolith, the powdery soil covering the surface, piled on top as radiation shielding. Cosmic rays and solar particles are a serious danger on the Moon, which has no atmosphere or magnetic field to protect against radiation. Several feet of regolith packed on top of habitats would reduce this exposure to acceptable levels. The base would include laboratories for analyzing samples, workshops for equipment repair and maintenance, greenhouses for growing fresh food, storage facilities, power systems using both solar panels and possibly small nuclear reactors, landing pads, and life support systems that recycle water and generate oxygen. Oxygen can be extracted not just from water ice, but from the rocks themselves through chemical processes. Lunar regolith is approximately 40% oxygen by weight, locked in minerals. Heat the regolith, add hydrogen or carbon, and chemical reactions can liberate that oxygen. This process, called in situ resource utilization, or ISRU, is critical to sustained presence on any world beyond Earth. The importance of lunar water ice cannot be overstated. Water is heavy, 8.3 pounds per gallon, and launching it from Earth to the Moon is expensive, currently costing thousands of dollars per pound. If astronauts can access water already on the Moon, the economics of lunar exploration change dramatically. Water is not just for drinking. Split it into hydrogen and oxygen through electrolysis, and you have rocket fuel. Use it for radiation shielding, grow plants in it, cool equipment with it. Water is the most valuable resource in space. The permanently shadowed regions at the lunar South Pole are thought to contain significant quantities of water ice, accumulated over billions of years. These regions have not seen sunlight since the craters formed, meaning temperatures remain below negative 250 degrees Fahrenheit, cold enough to trap water molecules. Or comets and asteroids that impacted the Moon over eons delivered water, and some of that water migrated to these cold traps where it froze and accumulated. NASA's lunar crater observation and sensing satellite mission in 2009 deliberately crashed a rocket stage into Cabeus crater and detected water in the resulting plume. Approximately 5% of the ejected material was water. That may not sound like much, but if the concentration is consistent throughout the crater, billions of gallons of water might be accessible. Mining this water is a technical challenge. The permanently shadowed regions are extremely cold and completely dark. Any mining equipment must carry its own power and lighting and must survive temperatures that make metals brittle and lubricants freeze solid. Several approaches are being studied. One involves drilling into the icy regolith, heating the drill rod to sublime the ice directly into water vapor, then capturing the vapor and condensing it into liquid water that can be stored. Another approach uses concentrated sunlight, reflected by mirrors from the crater rim into the shadowed region, to heat the surface and release water vapor. Yet another concept involves excavating large quantities of regolith, transporting it to a processing facility in sunlight, and baking the water out of it there. Whatever method proves most effective, the goal is the same: extract water from lunar ice, purify it, and use it to support human presence. Early missions will test prototype equipment on a small scale, perhaps producing just a few gallons of water to prove the concept works. Later missions will scale up, eventually producing tons of water, enough to refuel lunar landers and sustain a growing base. The Artemis program also includes extensive robotic missions under the Commercial Lunar Payload Services Program, or CLPS. This initiative contracts with private companies to deliver scientific instruments and technology demonstrations to the lunar surface. These robotic landers, much smaller and cheaper than crewed missions, scout locations for future astronaut visits, test equipment, and conduct science. Dozens of CLPS missions are planned for the coming decade, creating a sustained robotic presence on the moon that complements and supports the crewed missions. The international character of Artemis distinguishes it from Apollo, which was an American program with minimal foreign involvement. Artemis, by contrast, is a coalition. The Artemis Accords, signed by multiple countries, establish principles for a peaceful lunar exploration, including transparency, interoperability, emergency assistance, registration of space objects, release of scientific data, protecting heritage sites like the Apollo landing locations, and safe disposal of space debris. As of late 2025, more than 40 nations have signed these accords, making Artemis the most internationally cooperative space exploration program in history. Partners are contributing hardware, expertise, and astronauts. Canada is providing Canadarm3 and has secured crew positions on future missions. The European Space Agency is building Orion Service Module, Gateway's IHAB module, and Esprit, and in exchange will have European astronauts fly to the moon. Japan is contributing to IHAB and developing a pressurized lunar rover that will allow astronauts to travel long distances across the surface without wearing spacesuits, living inside the rover for days or weeks at a time. The United Arab Emirates is providing Gateway's airlock. Even countries without major space programs are contributing, paying for experiments, providing ground support, or training astronauts who will eventually fly. This cooperative model makes sense for multiple reasons. First, it spreads costs across many nations, making the program more affordable for everyone. Second, it leverages the expertise and technology of multiple space agencies, combining the best capabilities each has to offer. Third, it builds political support. When multiple countries are invested in a program, it becomes harder to cancel. Apollo died in part because it was purely American. When American political will faded, the program ended. Artemis, with partners around the world, has a broader base of support. But Artemis is not just about returning to the moon. From the beginning, the program has been explicitly designed as preparation for Mars. Every technology being developed for Artemis has Mars applications. The Space Launch System can eventually send heavy cargo toward Mars. Orion's life support systems are being tested for the kind of long-duration missions required for Mars travel. Gateway operations teach us about sustaining humans in deep space, far from Earth, which is essential for the 9-month journey to Mars. ISRU technology is being developed for extracting water and oxygen on the moon will be adapted for Mars, where water ice is also present, and where carbon dioxide in the atmosphere can be processed into oxygen and methane fuel. The moon is a testing ground close enough to Earth that problems can be solved without catastrophic consequences, far enough that it presents real challenges. A mission to Mars will last 2 to 3 years. The outbound journey, time on the surface, and the return, all constrained by the alignment of planetary orbits. There are no abort options. Once the spacecraft commits to the transfer trajectory, the crew is committed for the full duration. The psychological, physiological, and technical challenges are immense. Artemis allows us to work through those challenges incrementally on the moon before attempting the ultimate journey. Consider radiation exposure. On the moon, astronauts will experience higher radiation doses than they would on Earth or even on the International Space Station, because the moon has no magnetic field or atmosphere to block cosmic rays and solar radiation. But the exposure is manageable. A week on the lunar surface exposes astronauts to roughly the same radiation as several months on the ISS Artemis missions will gather detailed data on radiation exposure, test shielding materials, and develop protocols for monitoring and limiting dose. All of this directly applies to Mars, where astronauts will face similar radiation hazards for years instead of weeks. Consider life support systems. On the ISS, when something breaks, a resupply mission can bring replacement parts within a few months, or in emergencies, the crew can evacuate. Now, on the moon, resupply is harder, but still possible within days or weeks. On Mars, resupply is impossible for years, and evacuation is not an option. Life support systems must be ultra-reliable, easily maintainable, and capable of operating for years with only the spare parts the crew brought with them. Artemis missions will push life support systems to operate for longer periods with less resupply, approaching Mars mission requirements. Consider in situ resource utilization. On the moon, ISRU is a helpful capability that makes missions easier and cheaper. On Mars, ISRU is absolutely essential. A Mars mission cannot carry enough propellant for the return journey. The mass would be too great. The Mars Ascent Vehicle, which will launch astronauts from the Martian surface back to orbit, must generate its own fuel from Martian resources. Mars has water ice beneath its surface and an atmosphere that is 95% carbon dioxide. Through chemical processes, that carbon dioxide can be combined with hydrogen to produce methane and water. the water can be electrolyzed into hydrogen and oxygen. Methane and oxygen are a proven rocket propellant combination. NASA's Perseverance rover is carrying a demonstration experiment called MOXIE, Mars Oxygen, in situ resource utilization experiment that has already successfully produced oxygen from Martian atmosphere on a small scale. Artemis 1's SRU efforts on the Moon will scale up these technologies and prove they can support human missions. The timeline for a Mars mission remains uncertain. NASA has stated a goal of landing humans on Mars in the late 2030s or early 2040s, though this depends on technology development, budget, and political will. The mission architecture is still being refined, but the general outline is clear. Multiple cargo missions would launch first, delivering habitats, rovers, ISR equipment, and supplies to Mars before any humans launch. These cargo missions would take advantage of Mars's thin atmosphere to use aerodynamic entry, descent, and landing, heat shields, parachutes, and retro rockets to touch down safely. Once the cargo is safely on the surface and systems are operating, the crewed mission would launch. The crew would travel aboard a spacecraft similar to, but larger than Orion, possibly using nuclear electric propulsion to speed the journey and reduce the time astronauts spend exposed to radiation. Arriving at Mars, they would rendezvous with a pre-positioned Mars descent vehicle, transfer to it, and descend to the surface to meet the habitats and equipment waiting for them. They might spend 18 months on Mars, 1 Martian year, conducting extensive exploration before launching back to orbit in the Mars ascent vehicle, rendezvousing with the orbiting spacecraft, and heading home. The entire mission could last nearly 3 years, the longest and most challenging human space mission ever attempted. Artemis provides the foundation for this Mars mission. Every lesson learned on the Moon, every technology demonstrated, every procedure validated, brings us closer to the day when humans can set foot on another planet, 200 million miles from home, and know they have the tools and knowledge to survive and return. As you drift towards sleep, imagine being part of this grand endeavor. Imagine standing in mission control during Artemis 3, watching telemetry from the Moon as 2 astronauts take humanity's first steps on lunar soil in over 50 years. Imagine the moment when the first bucket of lunar water, ice, is extracted, melted, and purified, the first resource humanity has ever harvested from another world. Imagine watching the Mars mission launch years from now, knowing that everything learned during Artemis that made that moment possible. The Artemis program represents humanity at its best. Cooperation across nations, the pursuit of knowledge, the courage to face the unknown, and the audacity to believe that we can become a multi-world species. The challenges are immense. The costs are substantial. The risks are real, but so are the potential rewards. Scientific discoveries that reshape our understanding of the solar system's formation and the possibility of life beyond Earth. No, economic opportunities through space resources and technologies developed for extreme environments that find applications on Earth. Inspiration for a new generation of scientists, engineers, and explorers. And ultimately, the survival advantage that comes from spreading humanity across multiple worlds, ensuring that no single catastrophe can end our species. The Moon is not the destination. Mars is not the destination. The destination is the future itself, a future where Earth is humanity's cradle, but not our grave, where we venture outward to the stars, not out of desperation, but out of wonder, where the question is not whether humans will explore the cosmos, but how far we will go. Artemis is the beginning of that journey. When Neil Armstrong stepped onto the moon in 1969, he spoke of a giant leap for mankind. That leap carried us to the moon and back, and then we turned around and came home. We did not leap again. For 50 years, we stayed close to Earth, building space stations, launching satellites, learning to live and work in orbit. Valuable work, important work, but not the bold exploration that Apollo represented. Now with Artemis, we leap again. This time we leap not for a brief visit, but to stay. We leap not alone, but together, with partners around the world. We leap not to plant a flag and leave, but to build a future. The lunar gateway orbiting the moon. Bases on the surface, astronauts living and working on another world, mining ice from ancient craters, growing food in lunar greenhouses, learning lessons that prepare us for Mars, building infrastructure that makes deep space accessible not just to government astronauts, but eventually to scientists, explorers, and, yes, perhaps someday, to ordinary people who dream of seeing Earth rise above the lunar horizon. The path forward is not without obstacles. The Space Launch System has been criticized for its cost, over $2 billion per launch, making it the most expensive launch system ever developed. Some argue that commercial alternatives like SpaceX's Starship could accomplish the same goals more cheaply. These are legitimate debates, and the answers will shape the future of space exploration. But the fundamental goal remains: return humans to the moon and go beyond. Budget pressures will be constant. Every year, NASA must compete for funding against other national priorities. International partnerships help spread costs, but they also create complexity. Coordinating missions across multiple space agencies, different procurement systems, different safety standards. Technical challenges will arise, systems will fail, schedules will slip, costs will overrun. This is the nature of cutting-edge exploration. The key is perseverance, maintaining the commitment through setbacks and challenges. Political will is perhaps the biggest question mark. The Artemis program spans multiple presidential administrations, and space policy has historically been vulnerable to political changes. President Bush proposed returning to the moon with Constellation. President Obama cancelled Constellation in favor of asteroid missions and Mars preparation. President Trump resurrected lunar exploration as Artemis. President Biden has continued Artemis with modifications. The program has so far survived these transitions, in part because of its international character and bipartisan congressional support. But that support must be maintained. As you continue your journey into sleep, let these images fill your mind. The brilliant exhaust of a space launch system climbing toward the stars. The Orion spacecraft docked with Gateway, hanging in the black sky above the gray moon. Astronauts in their white spacesuits descending a ladder onto ancient lunar dust. Rovers kicking up rooster tails of dust as they explore valleys and crater rims. Habitats nestled on mountaintops, their windows glowing with warm light against the cold vacuum. And farther in the future, a spacecraft departing lunar orbit, its engines burning bright as it begins the long journey to Mars, carrying the hopes and dreams of everyone who has ever looked up at the stars and wondered. Artemis is humanity's return to the moon. But more than that, it is humanity's return to exploration, to pushing boundaries, to dreaming big. In 1961, President Kennedy challenged America to go to the moon, not because it was easy, but because it was hard. That challenge was met. Apollo succeeded, demonstrating what is possible when a nation commits to a goal and marshals the resources to achieve it. Now, we face a new challenge, even harder than Apollo because it asks not for a sprint, but for a marathon, not for a brief visit, but for permanent presence. The crew of Artemis 2, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, are training now, preparing their minds and bodies for the journey ahead. They practice procedures in simulators, study spacecraft systems, maintain peak physical fitness, and bond as a crew. They know they are making history. They know the risks, and they know that millions of people around the world will be watching when they launch, following their journey to the moon and back, inspired by their courage and skill. The crew of Artemis 3, not yet announced but already training, will have the honor and burden of being the first humans to touch the moon in the 21st century. They will walk in the footsteps of the Apollo astronauts while blazing a trail toward a future those pioneers could only imagine. They will see sights no human has seen, the stark beauty of the lunar South Pole, the shadows that have lain dark for billions of years, the peaks that catch eternal sunlight. They will conduct science that advances human knowledge. And they will demonstrate that we can build, live, and thrive on worlds beyond Earth. Artemis is more than rockets and spacecraft and budgets and timelines. Artemis is a statement about who we are and what we value. It says that we are explorers, that we seek knowledge, that we face challenges rather than retreat from them. It says that we can cooperate across borders, languages, and cultures to achieve goals beyond what any nation can accomplish alone. It says that we think about the future, that we invest in coming generations, that we dare to dream of a time when humanity is not confined to one fragile planet. Eugene Cernan, the last man to walk on the moon, left his daughter's initials traced in the lunar dust, TDC, for Teresa Dawn Cernan. Those letters are still there, undisturbed in the airless silence, protected from erosion by the lack of wind or water. They will remain for millions of years, a father's love recorded in regolith. Cernan said as he climbed back into the lunar module for the last time, "We leave as we came, and God willing, as we shall return." We are returning. Artemis fulfills Cernan's prayer and the dreams of everyone who watched Apollo and wondered why we stopped. We are returning to the moon, and this time we are staying. This time we are building. This time we are preparing for the next giant leap to Mars, to the asteroids, perhaps someday to the outer planets and beyond. As sleep takes you, picture the Earth rising above the lunar horizon as the Apollo 8 astronauts saw it, a beautiful blue and white sphere of life floating in darkness. Picture future astronauts seeing that same sight from Gateway, from surface bases, from rovers exploring far from their landing sites. Picture, years from now, astronauts on Mars looking back at Earth and Moon together, both just bright points of light in the Martian sky, a home receding in the distance as humanity ventures farther into the cosmos. Artemis, humanity's return to the moon. but also humanity's continuation of a journey that began when our ancestors first looked up at the stars and wondered what lay beyond the horizon. We are still those explorers, still driven by curiosity and courage, still reaching for the impossible. If you found this journey through the past, present, and future of lunar exploration educational and inspiring, please consider liking this video and subscribing to Sleep Edification for more immersive explorations of history, science, and human achievement. Share this with anyone who dreams of the stars. And sleep well, knowing that while you rest, teams around the world are working to make these dreams reality, building the rockets, training the astronauts, and solving the problems that stand between us and our destiny among the stars. Sweet dreams, and may your rest be filled with visions of worlds yet to be explored.